Today we're going to look at neuron activations and loss functions and how the activation of the output neurons in our network determines the loss function we should use. We're going to start by looking at the reasons for having a deeper network instead of just having a single hidden layer with lots of neurons. And then we're going to see one problem that arises from having a deep neural network, which is the vanishing gradients problem. And that will determine the usefulness of different types of activations in the hidden layers. And we're going to look at the rectified linear unit and variants of that type of activation and see why those are a good choice for activations on the hidden layers. And then we're going to look at the activations on the output layers and how they relate to different loss functions. So let's start with this question. There is this theorem, the universal approximation theorem, that tells us that we can approximate arbitrarily any function with a single hidden layer. So more specifically, more formally, suppose that we have one function that is non-constant, bounded and continuous, for example, the sigmoid activation function, and we have this function f that we want to approximate. This function f is continuous in some volume. So this is a hypervolume of a hypercube of side 1 in some dimensional space, and the number of dimensions here correspond to the number of dimensions of the function we want to approximate. In a particular example, it could be the function is a function that gives us the probability of some example belonging to some class, and then in that case the dimensions here would be the number of features we have. But let's suppose that this function is continuous and we are considering this volume here between 0 and 1 in all dimensions. In this case, then we can prove that we can find a finite number n of constants of this type, v, b, and this vector w, such that the weighted sum of instances of this function, for instance, the sigmoid activation, where the input is this product between these weights and the features, or the input vector, and also this bias, by finding the appropriate constants v, b, and w for all these n instances of our activation, we can approximate our target function within some arbitrary error, epsilon. So basically what we have here would be the output of a network with one output neuron and one linear output neuron and a single hidden layer. So you see, these, we can consider these factors here to be the weights of the output neuron, and these here would be the weights of each of the hidden layer neurons with this activation function. So basically what this proves is that if we have a single hidden layer and then an output neuron, we can approximate any function within some finite region. But this is not a problem, because simply by rescaling the inputs we can make sure that all our data is within that region. So this we do not lose the ability to generalize this for any problem. So basically all we need is one hidden layer in theory to solve any problem of approximating some function. The reason for using more than one layer is that we can have more oscillations, faster changes in the output of our network with the same number or fewer neurons by stacking layers. So basically, if we want to do everything in one hidden layer, we need a lot more neurons in that hidden layer than what we would need if we stack them to obtain the same kind of oscillations on the output. And these oscillations are related to the Vapnik-Chevronnenkin's dimensions. So to recall from last semester, the Vapnik-Chevronnenkin's dimension is the largest number of points that we can shatter with our hypothesis class. And shattering means being able to separate them regardless of labels. So for example, a linear classifier in 2 dimensions, we can put 3 points in a way that regardless of how we label them, so whether we put this one red, the others blue, or any other combination, or if 2 trivial cases would be all red and all blue, those would be trivial to classify. But with 3 points we can do this, and so we have this Vapnik-Strevonenki's dimension of 3 for a linear classifier in 2 dimensions. If we have 4 points, then we saw with the exclusive OR problem that we cannot solve it with a linear classifier. So basically, with the same number of neurons, if we stack them in a deeper network, we can have a greater shattering power, a greater power to classify, or in general to approximate some function, than what we would have with a single hidden layer. So even though in theory a single hidden layer would be enough, we can have fewer neurons and save on the number of parameters in our network by stacking them. In any case, remember that there is no learning algorithm that is best for all possible cases or better than all the other algorithms. So if we consider in theory all possible distributions of the data, then some algorithm that is better in some cases will be worse in other cases. This, of course, in real life, there may be algorithms that are more useful than others, because in real life data is not distributed in any logically possible way or mathematically possible way. Real life has some specific constraints, so some algorithms may in general work better than others, but in any case the best algorithm depends on the problem. So sometimes it may be better to use simpler algorithms and not deep neural networks, and you should be aware of this. So basically, when we use some very simple algorithms such as linear models with no nonlinear feature transformations, this could be, for example, logistic regression and so on, these tend to be better at memorizing some feature interactions, specific feature interactions, and they are easier to interpret because, for example, in a linear model, we have one weight for each feature, and we can immediately tell which features are more important for the classification, for example, or for the prediction we are making. So if we have things like customers who purchase this product also purchase this product, then these kinds of simple models would be best for that because they identify specifically the products that go together. What deep models can do much better than these simple models is to generalize for things that are similar. So when they create those internal representations, and we'll see a bit more about that in some future lectures, they can find things that have a similar pattern, even if we don't tell the model specifically on the features that those things are similar. However, they, because of that, because of being able to generalize and extract the relevant features, they tend to be harder to understand and interpret, and they may make some associations that we would not find correct. So this is an example of images that can mislead some image classification algorithms, but they can also mislead humans. We use basically the same kind of architecture in our own biological neural networks, where it's sometimes hard to see which ones are dogs and which ones are cookies or mops or bagels and things like that. And because of the patterns that we have and the way these images then are interpreted and encoded in the hidden layers, in the case of classification networks for these kinds of images, or even in our own brain, we may get a bit confused by these images sometimes. Okay, so basically the advantages of using deep neural networks, we have more shattering power with fewer parameters. We could in theory do the same thing with a very large hidden layer, a single hidden layer, but we would need a lot more neurons for that. And in the different layers, the network is learning to extract the appropriate features. So this is good for complex problems. Of course, you need to have enough data for this, but they allow these kinds of generalizations as the network is mapping into different representations. However, we need more data for deep neural networks than what we would with simpler models. And one problem is that when we look at what is happening at the hidden layers, at the different levels of the network, it can be very hard to interpret which features exactly the network is using. Because if we are designing the features ourselves, we understand what the features are. But if the network is learning the features automatically in those transformations, we may not be able to understand exactly what they mean or what they correspond to. Okay, so when we use deep neural networks, we have many layers, and then this problem can appear. The vanishing gradients problem arises because when we're doing backpropagation for training the network, we need to multiply all these derivatives. So we have the derivative of the error with respect to the output of the network, the derivative of that activation function, the output with respect to the weighted sum of the inputs, and then for each particular weight, and then we have to keep tracing back all these derivatives along the network. So since these are all multiplications, if we start having derivatives that are very small, very close to zero, then all of these values will start becoming very small, close to zero, and the product will eventually be so close to zero that training will stop. Because if the gradients with respect to some particular parameter are zero, we have no idea on how to change that parameter. We have no information for training the network. And this happens with activation functions that saturate, such as sigmoid, hyperbolic tangent, and so on. And you can see this easily if you go to the TensorFlow playground. You can experiment with different data sets and just quickly create your network, choose the activation functions, and so on. So if you use a sigmoid activation function with this simple example dataset, then we can just have one hidden layer with 8 neurons, and it works quickly. It trains in a few. This is after 300 300 epochs, but you can see that the error, the loss function went down very quickly. So it's easy with one hidden layer. If we have a more complex data set, for example, these spirals, then one hidden layer, in this case with only 8 neurons, is not enough. And if we add more hidden layers, training actually stops and we are unable to proceed. So this is after 1400 epochs, and we are still not classifying things well. And adding more layers will not help. Everything stops the training, so we are not able to solve this with these sigmoid activations. And the reason for this is that the shape of the sigmoid activation the output goes from 0 to 1, and the derivatives here at the extremities approach 0. So this starts becoming constant, and the derivative is very close to 0, and the same thing on this side. So as we move away from this central region, the derivatives start shrinking, and when we multiply all of these, then things will go so close to 0 that we are unable to train. So this is can be solved by using this rectified linear unit. So basically, with the sigmoid activation, we have this problem, saturation. Other activation functions that were traditionally used in neural networks, such as the hyperbolic tangent, have the same problem. So these are very intuitive when we think of the mathematical model of a biological neuron. It's good to have an activation function that fires after some threshold, and intuitively it seems nice to have it continuous, and the derivative is continuous and has this smooth shape. It seems to be an elegant solution for training neural networks. However, it has this problem that when we approach these regions, the derivative tends to 0 and everything bogs down. A rectified linear unit seems a lot uglier because it's this function that has below the threshold, so below 0, the output is 0. And if we are above 0, then the output is the same as the input. It's just this 45-degree line here that outputs x when we input x. So this seems to be a lot less elegant than those smooth functions, but the elbow here is enough to give it that nonlinear property, so that what is output from the rectified linear unit is not simply a linear transformation of the input because of this elbow here. This is much faster to compute. We don't actually have to do any complex computations. It's just a branch there depending on the value of the input. And if the neuron is firing, the derivative is constant at 1. So the derivative will not vanish for any neuron that is firing, and we can propagate it across the different layers without those problems that we had with the other activation functions. So this actually speeds up a lot the training of a deep neural network. You can try it here. For example, here in this case, we use 3 layers with a sigmoid activation, and even after 1400 epochs, we have no good results here. But if we change the activation to a rectified linear unit, then after 270 epochs, we already have our classifier working correctly, and everything trains quickly. This because with 3 layers, multiplying all those derivatives with the sigmoid activation made everything shrink down so much that training stopped. But with rectified linear units, then we don't have this problem, and training proceeds until the classifier gets everything right. And you can even add more layers. For example, with 4 layers, it still works quickly, 200 epochs, and we get the result. So basically, rectified linear units are much better for the hidden layers in deep neural networks than using, for example, sigmoid activations or hyperbolic tangent or that kind of activation functions that saturate. They are fast to compute. They do not saturate for those cases where the neuron is firing, and in those cases the gradient is always 1. So independently of how many layers you have, you can easily propagate the information from the loss function to all the weights using these activation functions. There is one slight disadvantage in rectified linear units because the neurons can die if training makes them always respond as 0 for all the training set. So you can see here in the function that in this region the rectified linear unit always outputs a 0, and so the derivative is 0. This is a constant value here. So if it happens that you have a neuron for which the weights make it always respond 0 for all the data that you are using in the training set, so at some particular time in training it got a configuration of weights that it always outputs 0, then this neuron is now dead because the derivative will always be 0 for those weights, and so the weights will not change and the situation will never improve. So this is a problem. Sometimes rectified linear units die during training, but it's not really that common because it must happen for all the examples in the training set. And if you have rectified linear units in deeper layers, then it also depends on the output of the previous layers and so on. So it's not really that bad of a problem, but it can happen. But there are variants to try to fix this problem, and the advantages of using rectified linear units greatly compensate these slight problems. So some variants to avoid this problem of rectified linear units dying when the output is always on this region is, for example, a leaky rectified linear unit. So the output is x or the same as the input when the input is greater than 0, but it's only a fraction of the input if the input is smaller than 0. So we still have this elbow here to give us the non-linearity on this transformation, but the derivative is never zero. It's smaller, but it's not zero on that side. So these tend to work better than the standard ReLU. Just one small point in TensorFlow. So this, in the original paper, this was the formulation. We divide the input by some constant. In TensorFlow, we multiply by some small value. So when you choose the alpha for the leaky ReLU, remember to choose a value that is lower below 1, so that it's a fraction of the input. The parametric ReLU is similar to leaky ReLU, but this is a learned parameter. During training, this alpha can be adjusted. Then we have others, randomized leaky ReLU for each example that is presented to the network. So each time we're going to activate the neuron, this alpha is drawn at random from some uniform distribution between a lower and an upper value. And then when we finish training, we freeze all the alphas at the average of the distribution. So this gives some randomness during training, and then it works like a leaky ReLU when we are using the network for predictions. You can see in this paper here an empirical comparison of different ReLU variants. Basically, a leaky ReLU seems to work best. But they all work fairly well, and the difference is not much. So in the exercises we have for today, you can experiment with variants of these rectified linear units. But the basic message here is that in the hidden layers, do not use activation functions that saturate, like sigmoid or hyperbolic tangent or such. Use rectified linear units or their variants. Otherwise, when you have several layers, training will stop and your network will not work. There are other more sophisticated variants. For example, the concatenated rectified linear units combine two rectified linear units that are symmetrical, so that we have this, the derivative here is -1, the derivative here is 1. And we have always an output on both sides. The exponential linear unit uses the linear output the same as the rectified linear unit for positive values, but then uses this smooth function, exponential function here on the lower part to make this the derivative continuous also on the function. This is more elegant, but in performance, I think we just pay an additional cost of this computation without any significant benefit, maybe in some particular cases, but in general it doesn't work better than rectified linear units. Okay, so these are several activations we can use, and when we are in the hidden layers, then all we need is to perform a nonlinear transformation of the input for that layer. So we need some nonlinearity on the activation, but ideally we need activations that are fast to compute and that do not suffer from the vanishing gradients problem. So rectified linear units and variations of rectified linear units are the recommended activations for the hidden layers. There are some specific networks. We're going to see some examples later on, like long short-term memory recurrent networks and so on, that use specific activation functions at some points, and those we do not change, we do not replace with rectified linear units. But if you're doing a multi-layer perceptron or a convolutional network or things like that, then rectified linear units are the best choice for the hidden layers. Of course, this is for the hidden layers. Then we need the output layer for our network. And here it depends on the problem that we're trying to solve. For example, suppose that we are trying to solve a regression problem. We want to approximate the output values of our network to some continuous set of values that we have in our data set. In that case, we do not want to artificially bound the output of the network to some interval. We want it to be able to adjust the values to whatever values we're trying to predict. So in this case, in a regression problem, we do not even want an activation function in the last layer. The last neuron should only have that linear combination of the outputs of the last hidden layer, and then output the weighted sum of those inputs. This way, by changing those weights, we can approximate any value that we need in a regression problem. In a binary classification problem, or these kinds of problems where we want the probability of having some class or some label, then the sigmoid activation is a good choice, because by varying between 0 and 1, we can interpret that as the probability of being, for example, in the first class, in case of a binary classification. Or if we have a multi-label problem. So a multi-label problem is different from multi-class in that one example may have several labels. So we can have an image that contains an airplane and clouds and ground and things like that. So we may want, instead of classifying the image in a single class, we may want to label all the different labels the image contains. So in that case, we can also use sigmoid activations. We use one neuron for each label we want to tag into our examples. And the sigmoid activation there gives us the probability that this label is associated with that example. So every time we are looking at binary choices, the sigmoid activation is a good option for the output neuron, because it gives us the probability that label or that class is assigned to the example. For multi-class classification, we use softmax. Note that multi-class is different from multi-label, because in multi-class problems, each example only belongs to one class. There are more than two classes, but the example can only belong to one. So what we need here is basically some function that out of all the possible k classes that we have, so there are k outputs here, but they all belong to the interval between 0 and 1, and the sum is 1, so that we can interpret this as the probability of belonging to each class. Suppose that we have 10 classes, then we distribute this probability among the 10 of them, and we can, for example, assign the example to the class with the largest probability, but this gives us the distribution of probabilities of belonging to all these classes. And this we can do with the softmax function. So this is the softmax function, and has this property. We output a vector of k values, where each of the values is between 0 and 1, so we can interpret that as a probability, and the sum of all these k values is 1. So this is the probability of belonging to any of the classes must be 1, because the example must belong to any class, to one class at least, and at most exactly one class, I mean. So this way we can model the probability of belonging to a class, and this is a good output activation for multi-class classification problems. So basically this is a generalization of the logistic function, that sigmoid activation, for multi-classes. So this is an important idea here. The output of the hidden layers, the activation of the hidden layer neurons should be chosen having in mind the ability of the network to learn. So we use rectified linear units to avoid losing the gradient information and being able to train the network. But the output layer activations are dependent on the problem we're trying to solve. So basically, for these three types of problem, regression, we do not have an activation function. We keep the neuron free. For binary decisions, whether we are looking at binary classification or multi-label problems, then we use sigmoid activation, because each sigmoid output gives us a probability between 0 and 1. And for multi-class classification, we use softmax, because this gives us a probability distribution over all the classes we are considering that tells us what is the probability of the example belonging to each of the classes, and then we can pick the one with the largest probability to assign the example to. Okay, so now let's see how this relates to the loss functions. Basically, we have a set of labeled data, this training set that we have in the case of supervised learning, and we want to approximate some function that maps the features to the target value that we're trying to predict. And we're going to do that by changing our parameters. For example, in a linear regression, we have a weighted sum of the inputs for the output, and we have these different weights that we want to parameterize. So this changing the weights can give us different lines, but we need to optimize some function to choose the best line. So for this, we are going to need some probabilities model, or some model of the probability distribution of our data. And in this case, we can, in the linear regression, we can assume that the output, the value we're trying to predict, is some function of the features plus a normally distributed error. So basically, our probabilities model is that the data points should be normally distributed around this straight line that we're going to fit. And we can also now compute, using this model, we can compute the probability of the data that we have by multiplying the probability for all the data points. And since our model gives us these probabilities by using this distribution here, we can compute the probability that our model is estimating for the data. So changing the parameters of our model will change the probability of the points being distributed in that way. And this is basically the likelihood of the set of parameters, and we are adjusting the parameters to try to maximize the likelihood. So our parameters are not random variables, but our data is randomly sampled from the universe, so we can talk about the probability of the data having that shape given our model. So our model, if we assume our model to be correct with some parameters, we can compute the probability of the data. Okay, so now we change the parameters in order to maximize the likelihood. So in this case, maximizing the likelihood would be maximizing the probability of the data given our parameters, but instead of doing all these products, we usually take the logarithm so that we can simplify this to sums. We can also ignore the probability of the features because these does not depend on the parameters for our model. Our model doesn't care about that, so these are this is a constant here. Then when we replace, so this probability, when we replace with the probability distribution that our model is assuming, we obtain a particular equation. So in this case, simplifying, we obtain this. So the maximum likelihood solution for linear regression is minimizing the quadratic error. So we have a minus sign there, and this is the square of the difference between each target value in our examples and the prediction of our model for that particular example. So if we sum all the differences squared and we adjust the parameters of our model to minimize that quadratic error, we obtain the maximum likelihood solution for this case. But note that the reason we reach this loss function is because we assumed this probabilistic model as a function of our parameters. So our model is a family of probability distributions that depend on the parameters we are assigning it, and we are choosing the probability distribution that maximizes the probability of our data, which is equivalent in this particular case to minimizing the quadratic error. But let's think now of this more generally. This is for the linear regression. We obtain this particular loss function, the sum of the quadratic errors, and then we minimize the loss function with gradient descent. So this we did for linear regression. But now let's look at the general approach by maximum likelihood. So in general, we have this data set that we drew randomly from the population with some probability distribution. And we also have in our model a family of probability distributions. In the case of linear regression, we have this family here. Depending on the parameters, we have this normal distribution around this straight line. But for different models, we can have different probability distributions depending on what we are trying to express with our model. Now we want to find the maximum likelihood estimate for this the set of parameters by maximizing the probability of the data that our model is estimating with those parameters. And intuitively we can think that if the data is drawn from the universe with some probability distribution, then we can maximize the estimated probability on our model, so this that we're trying to maximize here, if the probability distribution of our model given those parameters that we set is as close as possible to the distribution with which we obtained the data. So basically we want our model to match the data as well as possible. We can also do a simplification here. Instead of doing this product, we can take the logarithm and the sum of the logarithms, because the maximum will be on the same place. So the values of the parameters that maximize this product here are exactly the same as the parameters that maximize the sum of the logarithms. So this removes all those products there. And we can also simplify this if we divide, say we have m examples in our training set, but if we divide the result by m, which is just a constant and doesn't change the value that maximizes the expression, we can convert this into the expected value. So basically what we want to maximize is the probability that our model is assigning to the data, or more specifically the logarithm of that probability, that on average we get when we sample data using this probability distribution that the universe has set for us. So when we are measuring the data to obtain a data set, we are following this probability distribution that the data must follow due to the constraints reality imposes. So we can look at this in different ways. One way of trying to match the probability distribution given by our model and the probability distribution the data has is to look at the divergence between the two distributions. For example, the Kullback-Leibler divergence measures these differences between probability distributions, and it has this this formula here. So basically we are looking at the difference between the logarithm of the probability of the data and the logarithm of the probability given by the model. But since the probability of the data does not depend on our parameters, only the model depends on the parameters we're trying to optimize, this ends up being the same thing. Minimizing the divergence between the two is the same as maximizing the logarithm of the probability here, because of this minus sign here. Or we can also see that in this case where one of the terms is constant because it doesn't depend on the parameters, this is also equivalent to minimizing the cross entropy between the two distributions. So between what our model is saying and what the data is. And this is why it's often the case that you find minimizing the cross entropy as a description of what we're trying to do when training the network. There are some loss functions that sometimes are specifically called cross entropy, like the logistic loss function and so on. But the idea is always the same. We are trying to match the probability distribution given by our model to the probability distribution of the data. So the match between the two consists in minimizing the divergence or minimizing the cross entropy between the two. So this is what we do in all cases when we're trying to find the loss function. In the particular case of supervised learning, usually these probability distributions are conditional probabilities because we're trying to predict some label based on the features. In unsupervised learning, it can be just the distribution of all the data in general, so it depends a bit on the kind of problem we're solving, but the approach is always the same. Maximizing likelihood, which means minimizing the divergence between the distribution of the data and what the model is predicting the distribution to be, so minimizing the cross entropy between the two. However, the important part here is that even though this is always the same idea, the resulting loss function will depend on exactly what is the probability distribution our model is trying to express. So, for example, for linear regression, when we assume that the probability distribution, the conditional probability of the target value given the features, is a normal distribution around this linear function that we are using for the linear regression, we applying this maximum likelihood principle, minimizing the cross entropy between the distribution of the data and what the model is telling us, led us to the minimization of the quadratic error. So for this particular model, we obtain this loss function. If we consider a different model, for example, in logistic regression or in a sigmoid output of a network to predict the probability in a binary classification problem, then what we have is the output function of our network is the probability of belonging to class 1 given the features. So in this case, the expression for the likelihood is different. We are going to multiply all these probabilities. We take the logarithm, the sum, and so on, and we obtain this loss function. So this will be the cross entropy, the loss function corresponding to minimizing the cross entropy in this particular case, but it's different from the one in a linear regression because the probability model that we are using is different. So this would be this logistic loss function that we use in logistic regression. The same thing for multi-class classification. So if we want to find multi-class classification for n classes, then we use the softmax output and we use the softmax cross entropy loss function here. So basically, the important message here, aside from all of these details, is that the output of our network will depend on the kind of problem we're trying to solve. If we are solving a linear regression, if we are solving a regression problem, we need a linear output so that we do not restrict the possible values the neuron will output. And in that case, we have that probability model that the true values is our prediction and some normal distributed error, and this means that we use the mean squared error to as the loss function to find the maximum likelihood solution. When we have a binary classification, then what our model is outputting with the sigmoid activation is the class probability, and in that case we have this logistic loss function here. It's again minimizing cross entropy, maximizing likelihood, and so on. The objective is the same, but since the probability model is different, the specific loss function is different too. And for n-ary classification, we have the softmax cross entropy. So the important thing to retain here is that you cannot just pick at random a loss function for some problem. You need to think about not only the activation on the output neuron, but also what is the appropriate loss function for that particular problem. In some cases, if you pick the wrong loss function, it may still work. For example, you can do binary classification using mean squared error because the minimum will tend to be on the same place. It will not be as efficient in training, but it may work. However, it would not be correct to do so because there is no reason, no justification to pick the wrong loss function. In some cases, you would get a completely wrong result. For example, if you try to solve a regression with a logistic loss or something like that, then everything will go wrong because it really makes no sense in those cases. So remember, pick the output activation and the loss function correctly when you're trying to solve some problem with neural networks. So to sum up, we saw the differences between a wide and shallow model, like a neural network with only a single layer, and deep neural networks. Basically, even though in theory one single hidden neuron layer could solve any problem, in practice it's best to have deep networks because they have greater shattering power with fewer neurons, and so things tend to work better that way. However, this creates the vanishing gradients problem, and so we solve it by using activations in the hidden layers that are like rectified linear units or their variants to prevent saturation and loss of the gradient information. We also need to think about the activations for the output layers, and these depend on the problem we're trying to solve. And depending on the specific activations, we need to choose the correct loss functions too. So always be aware of this. Think about your problem, see what the output of your network should be, and then choose the appropriate loss function depending on that. You have a lot more detail about this on these chapters on the deep learning book. So some of the details go outside the scope of the course, but it may be a good idea to take a look because it explains these things in more detail. You should also take a look at the documentation of TensorFlow for the activation functions so that you see which ones are already available and that you can experiment with. We're going to see in the exercises in the next lecture, and then you can try different activation functions. So let's take a short break and we continue at 5 minutes to 10 in 9 minutes. Okay, see you soon.